So, we saw in the last lecture that the resolving power of a grating is proportional to the product of n m of the number of illuminated grooves. N is the number of illuminated grooves and n the diffraction and the diffraction order m. Okay. The more grooves that are hit by the laser beam, the better is the spectral resolution. Okay. And also the power density without a beam expansion might be high enough to damage the grating surface. Okay. So, two uses of expanding the beam. One is of course, you get a better resolution, and the other is if you expand the beam intensity becomes a little less on each of these grooves or the surface of the grating. So, these are the techniques used in making or building or designing a laser cavity. So, now I will just go to what spectroscopists require. Okay. Generally how do we describe any spectroscopic experiment? What does the spectroscopist want from an experiment? Okay. So, he has some material, and in the material he may study the absorption, fluorescence, or he can study, or he can detect photoelectrons. Okay. So, it could be generally he is studying say 2 levels, I will take 2 levels. He will put a light and he will see something from some molecule from here to here, or some atom has gone from here to here, and immediately he is able to detect this is kind of absorption, or there could be an emission from this top level to the bottom level, and the spectroscopist will record this emission, and he knows, and he has an idea of what is the energy level of what are the energy of these levels. He knows the distance between the 2 levels through these kind of experiments. So, this is kind of direct absorption or direct fluorescence, but you could have multi-photon absorption processes too. That also is a big asset for the spectroscopist. Okay. So, material multi-photon interaction is usually detected through direct absorption fluorescence, ionization current, or a photodetector detection system. The excited state structure of these materials in gases, liquids, or solids, such as electronic, vibrational, or rotational states, or fine structures which are not found in ordinary single photon spectroscopy. This can be seen in a wide frequency range from lower electronic excited states to ionized continuum. Okay. So, there are you can do direct absorption, but still you may not see certain energy levels which may be hidden within one. There can be fine structures here. You may think of it as one upper level, but then actually there are finer structures. You might miss out on those. So, quite often multi-photon absorption is done, or you can tune the laser. You tune the laser. So, you have a lower level here, and you can have one wavelength which goes up here, or one wavelength which absorbs and goes to this level, or the next wavelength which goes up to the top level. So, you can distinguish between these finer levels. Now, what do you need for that? For that you need a tunable laser. So, you should be able to tune from lambda 1 to lambda 3. Okay. So, you should have 3 wavelengths, and in your lab you should be able to do it with your laser. That is why we need tunable laser. And dye laser is a fine example of getting tunability over the visible wavelengths. But then you can get tunability over the infrared wavelengths also. That is also used by the spectroscopists. Okay. So, you can get carbon dioxide laser which you can tune in the wavelength band of 9.4 micrometer or 10.6 micrometer. These are all carbon dioxide laser bands. So, there is a tuning range in this 9.4 micrometer range, there is a tuning range in 10.6 micrometer range. So, the spectroscopist wants to use that, he wants to tune it, and he wants to tune all these wavelengths in order to know each of those structures that are available in that material. He wants to study that material completely. So, for that he needs to know all the energy levels that are possible, and he can do that experimentally with this. So, this is in the infrared, a tuning range in the infrared. In fact, you can get a tuning range in the infrared, with semiconductor laser. If you recollect the semiconductor laser studies that I had taken a few lectures before, gallium arsenide, gallium indium arsenide, and many of those semiconductor materials, they gave out wavelengths in the infrared region, most of them. Some were okay in the ultraviolet and all, but most of them they had infrared. So, the tuning in the infrared range, say, is covered by carbon dioxide and say semiconductor laser. Then you have the excimer laser. Excimer lasers covers wavelengths in the ultraviolet range. Okay. So, for a spectroscopist, he needs all of them. Depending on the materials he is going to study, he is going to buy a tunable laser either in the visible, which may be like dye laser. He can have a tunable laser in the infrared, which may be a carbon dioxide laser or a semiconductor laser. He may want the wavelengths in the ultraviolet range, then he looks in for the excimer laser. And there are many other methods, of course, of getting this tuning thing, but it is an important thing for a spectroscopist. Now, okay, I will come back to multiphoton processes. So, in multiphoton processes, what you can have is, you can have here a non-resonant 2-photon absorption. Okay, so, I can have, this is the ground level, from the ground level you have one photon which is going up here, and this looks like a virtual state, not a real eigenstate. Sometimes you do get materials which are like that, I mean they are not the real states like this. Okay, that is why it is shown in dashed line. And again from here you can have another photon. Another photon, by the way, see, they are of different wavelengths or different frequencies. So, I have one photon of frequency nu 1 and another photon of frequency nu 2, which manages to take my system from this ground level to this upper level. Okay, and this is called non-resonant 2-photon absorption. It is non-resonant because this ground level to this level, which is the real state, you do not have one frequency. It is not resonant. The frequency or the wavelength of the laser that you are using to excite to this level is non-resonant. You are getting two different photons to add up and go up here. Okay. So, you do get such kind of processes. So, experimentally people have seen nu 1 plus nu 2 will give me a state which is here. So, in order to explain that there is no real state here, so this has to be a virtual state. Okay. Quite often in many spectroscopic experiments, you do get these virtual states. We will describe a little bit more about virtual states later on. Let us understand another multiphoton process. Okay. So, another multiphoton process is here, a resonant 2-photon absorption. This was non-resonant, this is resonant. Resonant because you have actual eigenstates here, 1, 2 and 3 this is ground level, first eigenstate, second eigenstate. Okay. The real energy levels, real eigenstates. So, that means I need a photon with a frequency nu 3 You can say it in terms of lambda also, but I am just talking in terms of frequency. So, you know frequency and lambda are inversely proportional to each other. So, I need one photon which will take the system to this excited level, then I need another photon to take, which is of a different frequency, to take it to this level. And since these are real eigenstates, it is called resonant two photon absorption. Okay. That means the laser light is resonant with these, with this energy gap. Then there is a 3 photon ionization. Why do I call ionization? Because here I am going from one state to the next, it is not ionized, it is in an excited state. Okay. It is in a very big excited state. But here if you see, I have one photon which has come to this virtual state, then you have the next photon which goes to the next eigenstate, and then you have another photon which takes it to a continuum. A continuum means all the energy states are very closely spaced. So, it can go to any of these, it is as good as having just one state there, though it is composed of many states, all those photons go up to this state. Okay. And once it comes to this continuum, it is as good as being ionized. So, it could be a molecule, it could be an atom, it has become ionized here. Okay. So, this is the multiphoton process. Okay. Now, the multiphoton process has a lot of variation and lot of use. Why don't I look for only a resonant process, and that too resonant, not 2 photon, but going from here to directly here. Okay. Why do I look for that? Okay. That I will explain it to you. Generally, it is used for isotope separation. That is a very sought after separation process and specialized by many spectroscopists. So, why do I need to know that? Now, the problem is when I speak of isotope separation, okay, that is the whole idea. Means I want to separate the isotope of the same element, I want to separate them out. For example, I have just taken this example of silicon fluoride, SiF4, where Si28F4 is the most abundant, 92% is available in nature, okay. And SiF429 is 4.7%, all available in nature. You know, when you take silicon fluoride, it comes with all these 3. Okay. And so, what is the isotope? Here this is 28, 28 is the nucleon number in the nucleus. That means silicon has number of protons is equal to 14. Okay. So, number of neutrons plus protons will be 28. Okay, that is the usual case. But in the next isotope, here it is 29, that means one more neutron exists. Proton will remain the same, 14, because it has to neutralize those electrons which are revolving around. Okay. So, 29, you have one more neutral particle which makes it 29. If you have 2 more neutrons, then it becomes 30. Though the occurrences of these 2 are a little less as compared to this, okay, you will not even notice. In a usual say chemical reaction, you will not even notice them. In standard chemical reactions with other materials or even ablation or so many other kinds of processes, or when you see that silicon fluoride altogether, you will visually or through a microscope or whatever, you will not be able to make out. but there are subtle differences between these isotopes. And in the electronic industry, I believe they want silicon fluoride or silicon 28, which is the most abundant. You've got 92%. But if you remove these completely, this will become close to 100%. So you have to find ways of removing this 29 and 30. I believe if you do that, if it is absolutely pure silicon 28, then the thermal conductivity becomes very good of silicon. And there are a few other parameters which I do not know of, but there are a few other parameters which is required in the electronics industry. And so they are interested in the isotope separation of silicon. Okay. So they want 100% of silicon 28. Now how can this be done? This can be done by multi-photon dissociation. Okay. Exactly following the same principle. You have multi-photons to dissociate silicon, take it to this continuum and just dissociate it. Okay. So let us see how it is done. So silicon fluoride, I mean, you know, it is like this silicon, and this is a bond, this is a bond, this is a bond. 4 fluorine bonds are there. Okay. So if you are able to break one of these bonds, okay, it gets ionized and it goes. But you won't want to break any bond. You would like to separate out these silicon. In this silicon, 28 exists, 29 exists, 30 exists, everything exists. But you want to select, say, only 29 and remove it. Or you want to select only, say, silicon 30, which is 3.1%, and remove it. So what would you do? I have this molecule. Molecule and I target these bonds here. These bonds are vibrating bonds. They are all vibrating. The moment they get energy, they start vibrating, rotating, all that. And I have shown all these vibrational bonds here like this. Energy levels, sorry, not bonds. These are the bonds, and when they vibrate, these are the energy levels it creates. So it from sparse density from sparse density to very densely placed energy levels, and finally this part is the continuum where you know, they are so closely spaced, it's as good as a dissociation. Means the bonds have broken somehow or the other, and you can go to any level and the bonds have broken. So how is it done? Here in case of silicon fluoride, they use an excitation laser, which is actually an infrared laser. And because these bonds are vibrational bonds, so it's likely to be, the excitation is likely to occur with an infrared laser. So I have an excitation laser here, which is shown in this color. And then once it has reached this kind of excitation, then I dissociate this part. This laser is used for dissociation. It's already excited here. All you need is a little bit more energy to absolutely break the bond and dissociate it. Okay, so this part is a dissociation level. So all this, it will come here and the bond is broken. So here I show the infrared absorption spectrum of silicon fluoride. The arrows indicate the vibrational frequencies of different isotopic species. Bars correspond to the excitation and the dissociation wavelength. Here a carbon dioxide laser is used. Here when I say arrows, these are the arrows. This is for the most abundant, that is silicon 28, and this is the absorption line, of course. This is the absorption. These are the wavelengths. Okay. And this is the absorption here, absorption of silicon 30 and silicon 29. So the absorption of silicon 28 is quite high. So, it is very easy to do that, either you take that out or you remove these, whichever way, whichever wavelength is you are able to tune to whichever wavelength. By the way, just have a look at the units of wavelength that is given here. Quite often in spectroscopy, this is the unit that is used, centimeter inverse. Okay. It's till now we have been talking about lambda in terms of nanometer, centimeter. So, this is given as centimeter inverse. So, you just take 1 upon lambda and that will give it to you in centimeters or nanometers, meters, whatever. So, it is just 1 by lambda. So, this is a unit which is used quite often in spectroscopic terms. Okay. So, okay, the maximum excitation laser can be this 9.7 micrometer or for carbon dioxide. So, here as I have said, carbon dioxide has something in the 9.4 micrometer band and it has another band in the 10.6 micrometer band. So, this blue line corresponds to 9.7 micrometer, which can be used as the excitation laser, and this part 10.1 micrometer can be used as the dissociation laser, a dissociation wavelength. Okay. So, once you have these two wavelengths, these bonds break up and they are there. So, when the bonds break up, what is the chemical equation? SiF4 with the effect of H nu gives SiF2 plus 2F, or it could even give these two F and these two bonds have broken, or it can be SiF3, Si and F3 and one bond is broken and one fluorine, and you can have SiF plus 3F, SiF just this and 3 bonds have broken. It can be any of these with the help of a laser light with energy H nu. And once you have got them dissociated like that, you can use some scavenger elements, as they are called, to react with SiF2 plus, that is a ionized state, SiF3 plus is an ionized state, SiF plus is again an ionized state. So, you can use some other element to work with that and you separate it out. You already made the separation of the isotopes at this level, at the excitation and dissociation level. This is just one way of collecting up the dissociated particles. So, by this method of multiphoton dissociation, you are able to separate out isotopes of silicon. That is why it is called isotope separation. Actually, the main when did this isotope separation first, when did people start trying to do isotope separation? When they wanted to separate uranium. Uranium 235, that was the push point when they started calling it isotope separation. Before that, it was multiphoton dissociation. Multiphoton dissociation of carbon isotopes have been also done in many experiments, but the main push came because people wanted to separate out the isotopes of uranium. Okay. So, and quite often it is called laser enrichment method. Okay. Why is it called laser enrichment method? Because in case of uranium, here I show the isotopes of uranium, uranium 235, 238 is the most abundant, that means it is 99.3%, and uranium 235 occurs in natural form in 0.7% only. But in a nuclear reactor, you need uranium 235. So, you really have to do a lot of separation. It is only 0.7%, you have to make it 100%. Okay. So, it is a difficult job actually for uranium. In fact, as the elements get heavier and heavier, you see uranium is heavier than silicon. Okay. The line separation is the line separation means energy level separation is very little. So, tuning your laser to those particular energy levels and those wavelengths, it becomes very difficult. Okay. So, here uranium 238, I said 92 is the number of protons. Okay. 92 is the number. So, there should be 92 neutrons too. But it is a little more or less, okay, the number of neutrons. That is why you get uranium 235, uranium, all these things come into the picture. Okay. Here 143 neutrons and 146 neutrons are there in one. In uranium 238, 143 neutrons, uranium 235, 146 neutrons. Okay. So, this is called, and it is called enrichment, because as I say the actual substance of uranium is not rich in uranium 235, but you want to make it rich in uranium 235 and eliminate 238. That is how it becomes enriched. Okay, that is the whole idea. It is again a multi-photon process, same as I have described before, but it is called laser enrichment method, and it can be done with lasers only, there is no other way.